to be able to participate in this e-meeting on the occasion of the 80th anniversary of the Metallurgy Department. Well, I've been already introduced, but let me tell you, I graduated from B College Metallurgy Department in 1964. Well, I did my bachelor's, my master's, and also my Ph.D. from the same institute, and served that institute for 11 years, and then shifted to IIT Kanpur. And a second stint, again from 2014 to 2019, in the School of Material Science. So you see that my life started from BE College, and at the end of my career, I was again back to BE College. So that's very interesting. Now, so far as today's talk is concerned, I have chosen an area which does not strictly belong to metallurgy as such. But there is a reason why I have chosen that. Part of it, of course, is metallurgy, but part of it is mechanical engineering. Now, let me start with the slides, and I'll explain why I have done so. Can I have the slides, please?
Yes, sir. I'm presenting, sir. Sir, is my screen visible?
Not yet.
Not yet. Yes, yes.
Yes. Can I go to the first slide, please? Yes. Yes, that's the one. You see, the topic of my lecture is additive manufacturing of high entropy alloys. There is a reason why I've chosen this subject. Can I have the next slide, please? You see, this is an area where the mechanical engineer and the metallurgist have come together. The modern metallurgy, as we know about, was, modern metallurgy, as we know about, started from, say, about 1940s. The reason was rather strange. You know, that was with the invention of the jet engines. The mechanical engineers reigned supreme during those days, and they built all kinds of machines. The metallurgist was a bit subdued. Now, while making the jet engines, the mechanical engineers realized for the first time that material may be as important as design. And therefore, they called in the metallurgist to help them out. And that is how the golden days of metallurgy began. Now, can I have the next slide, please? The next slide, please.
Sir, I think it's being updated.
Yes. Right. You see now, yes. You see, the present situation is such in our country that in industry, people will prefer hiring a mechanical engineer with some knowledge of metallurgy than a metallurgist. In many industries, it's happening like that. The reason is we have not changed much from where we started. You see, if metallurgy has to survive, the metallurgist has to venture out into other areas. For example, the most important area where a metallurgist can go to is the area of manufacturing science and engineering. And as you know, that additive manufacturing is a new way of manufacturing, which is capturing the imagination of all engineers. And this is also very much dependent on the nature and properties of materials. So this will be an area where the metallurgists must jump in, and don't leave this area entirely to the mechanical engineers. So metallurgy has to change. That's what my feeling is. Now, additive manufacturing, is an area where complementary roles are played by the mechanical engineer and the metallurgist. And we know what additive manufacturing is. It's a process of building up a three-dimensional object from a computer-aided design or CAD model. This is usually done by successfully adding material layer by layer. The term 3D printing is increasingly used as a synonym for additive manufacturing. Can I have the next slide, please? Yeah. Well, the method, is simple. What you do, you have a platform, a building platform, and you apply a thin layer of the powder of the material to be manufactured onto the building platform, and then you get it fused or melted by using a powerful laser or electron beam, and the whole process will be dictated by a CAD program. Then the platform is lowered, another layer of powder is applied. Once again, the material is fused and made to get welded with the layer below. This is continued till the final product is manufactured as per CAD. Well, these are two diagrams showing on the left-hand side. It is a electron beam equipment, and the right-hand side is the laser equipment. Next one, please. Yeah, these are all the different parts, so it's not very important. Yes, please. Next one. Yeah, so you see that if you look at the area bordered by thick black line, the one at the left is the design produced by computer. It's a CAD design on the left. And the one to the right is the final shape of the material to be manufactured. Then we come to the right-hand side. So what we do, the CAD program is used to dictate the whole process, so that in the first figure in the right, you'll find powder is added on the platform, and then it is fused. Next slide, please. Yeah, and this process continues till the whole substance is manufactured as per the CAD program. So you see, here is a case where the design dictates the product. Next slide, please. Now, why we go for this additive manufacturing process? There are several points to be considered. Strength of additive manufacturing, manufactured products lies in those areas where conventional manufacturing has reached its limit. It's of interest where new approach in the design and manufacture object is required. Then AM enables design-driven manufacturing. You see, rather than the other way around, highly complex structures can be easily produced by this method, and it provides high degree of design freedom and integration of the functional features. Next slide, please. So what are the requirements of materials for AM? You see, materials which can be processed by AM must meet two main criteria: good weldability to avoid cracks during solidification, and raw materials are very important. These must be available spherical powders with the size of a few tenths of microns in order to achieve good packing density and homogeneity. Next one, please. So what are the characteristics of these AM products? The most important thing is here you can achieve a very high cooling rate and directional solidification, which you do not get in the cast materials. Grains are much finer here, but there are some bulk defects as well as surface defects also. Next one, please. Yeah, you can produce various kinds of microstructure in an AM product. So this is one. You can see the columnar structures. The next one, please. The next slide. Yeah, you can have a microstructure of this type. Next one, please. Can I have the next? Yeah, you can have this. You can have columnar grains and equiax grains. Side by side. So the different types of microstructural architecture can be achieved by this process. This is a unique characteristic of the AM process. The next one, please. Yeah, this is again another microstructure. Next one, please. Yeah, so just to show you that you can really get the microstructure of your choice by controlling the parameters. Next one, please. Yeah, this shows that you can easily find out the process window necessary. So if you want to have fully dense material, you choose this is for the selective laser melted process, laser power and scan speed. So the processing window can be found out by trial and error method. Can I have the next, please? Yeah. Again, you can control the microstructure by controlling the parameters like the thermal gradient and the solidification rate velocity. Next one, please. So in this particular case, in a normal case, we have a property pyramid where the four corners are, as you can see here, properties, then processing, then structure and performance. Now here you add another dimension, which is the microstructural architecture. So this way, the AM products differ from products which are normally made by usual methods. Next slide, please. Yeah, these are some of the things made by AM, some orthopedic pedic implant. Next one, please. Yeah, some of the defects in AM products like pores and tears, etc. Next one, please. Yeah. So what is the mechanical behavior of this product? Because of different bulk and surface structures in AM products, the mechanical properties may differ substantially from conventional process materials. The prime necessity, therefore, is to better understand the complex relationships between the metallurgical characteristics of powder feeds and their effects on processing, microstructure, and mechanical properties. Next slide, please. Well, this is, these two diagrams show the material's property space. The y-axis is yield strength and the x-axis is elongation. The dotted lines show materials which are made by the existing process. The farm lines show areas where materials are made by the AM process. So you can see the much higher versatility of the AM process. You can have a whole range of properties by using the AM method. Next one, please. And if you look at the property, the bottom one is for the wrought material. It's a wrought, I think, stainless steel, doesn't matter. The upper ones are all made by the AM process. You can see higher strength and very good elongation also. Next one, please. Yeah, so typically, these AM metallic products have been attempted till now. Nickel-based superalloys, cobalt chromium alloys, stainless steels, titanium-based alloys, intermetallics, low alloy steels, refractory metals, etc. The next one, please. You see, now I will consider the high entropy alloys. We know that, what is the method of, this additive manufacturing is. So the topic of my lecture is additive manufacturing of high entropy alloys. The reason why I've chosen this area is I have started working in this area from last year, and I'm really fascinated by this area. Now, what are high entropy alloys? These are rather recent, as I said, and the first result was published in 2004. So these high entropy alloys can be defined both on the basis of composition and configurational entropy. So what is the composition-based definition? So these are alloys composed of 5 or more principal elements in equimolar ratios. You see, as metallurgists, we are aware of alloys where we have got maybe one solvent where a few other solutes are added. So the main component is the solvent, and the solutes, they are take a minor part. But here, this is totally different. Here, the alloys are composed of 5 or more principal elements in equimolar ratios. Later, of course, this definition has been changed. So nowadays, high entropy alloys are those where the concentration of each element is between 35 and 5 atomic percent, and there may be some minor elements also to modify the properties of the base. Next one, please. Can I have the next slide, please? Yeah. So what is the entropy-based definition? These are alloys that have relatively high configurational entropy. So how high? Greater than 1.5 into the universal gas constant. So high entropy alloys possess superior properties, such as remarkable combination of high yield strength and ductility, good microstructural stability, and can retain mechanical strength at elevated temperatures, and are highly resistant to wear, fatigue, corrosion, and oxidation. Sometimes these are also referred to as complex concentrated alloys, CCAs. Next one, please. So,
Updating, sir.
Pardon? Yeah, I got it. You see, there are 4 core effects which are often used to describe the high entropy alloys. One is the high entropy. The second one is high lattice distortion. You can see that if there are 5 or more principal elements, there will be a lot of distortion in the lattice. And the third one is very sluggish diffusion. And the fourth one has been named the cocktail effect. The name was given by Professor S. Ranganathan of IIT Bangalore. So the cocktail effect means exceptional materials properties often result from unexpected synergies. You see, this is an area where although a lot of work has been done, but a lot more needs to be done because the entire fundamentals are not clear yet. So cocktail effect is one of those areas, where really a lot more work has to be done. Well, this shows, when instead of one principal element, you have many principal elements, lattice distortion will take place, etc., etc. The next one, please. Now, what is the effect of the high configurational entropy? If you have a high configurational entropy, the simple solid solutions such as BCC, FCC, and HCP will be stabilized. However, in many cases, the best balances of properties are achieved for microstructure consisting of a disordered solid solution phase and an ordered multi-component precipitate phase. Next one, please.
Updating, sir.
Yeah. The 2 major new concepts emanating from the development of the high entropy alloys are: this apparently opens a vast unexplored realm of alloy composition potential to influence the solid solution phase stability through control of configurational entropy. So these two distinct ideas have captured the imagination and efforts of the material science community all over the world. You see, you look at the multitudes of alloys you can have, where because the number of main elements is 5 or more. So this is a classic case where the metallurgist can use the knowledge of materials informatics, artificial intelligence, and high level of data processing, data mining. So these are most important that the metallurgist can go through. So you see that metallurgist nowadays, he or she has to learn a little bit of manufacturing, a little bit of computer science, and whatnot. So metallurgists must come out of their cocoons and try to diversify themselves. Now, yes. I think we can skip that. The next one, please. You see, one of the applications, can I get back to the previous? One of the applications is, the high entropy alloy coatings. These alloys can be used as coatings on existing materials. For example, gas turbine engines. And these coatings are very hard and they last for much longer. And there again, the properties, the material property space for such coatings have been given here, Vickers hardness along the y-axis and density over here. So you can see that you have a large materials property space to choose from. So this is the beauty of these materials. The next one, please. Yeah, it's the same thing like the previous one. We can go to the next slide, please. Yeah, this is a summary of various processing conditions which are applied to produce these coatings. You can skip that. You can have the next one, please. Yeah, it is also the summary of properties and phases in laser-cladded HEA alloys. Now, in addition to coatings, we also produce high entropy alloys in the bulk form. So the idea to use AM technique for producing bulk HEAs is based on the premise of avoiding slow cooling. You see, in the AM process, the biggest advantage is avoidance of slow cooling, which is common in case of arc melting or levitation melting during solidification. Due to this, the interdendritic segregation in the microstructure is minimized and the solubility limitations are avoided. So this is very interesting. The most studied high entropy alloy system made by AM has been based on the aluminium, cobalt, chromium, iron, nickel system. Look at the yield strength, UTS, and percentage elongations of the as-built, laser melted HEA. Yield 600 MPa, UTS 745 MPa, percentage elongation 32. And look at the comparison with that for the as-cast material the normal way, where the yield is 188, UTS is 457, and of course, the elongation is more, 50%. So the considerable enhancement of the mechanical properties of the AM product is unlikely to be explained by the grain refinement of the former due to a much faster cooling. A lot of people try to give an account for the exceptional strength by looking at the finer grain size, but they couldn't explain it. So there are things other than fine grain size which must be considered. The next one, please. Well, again, there's the microstructures that you get in such steels. We can skip that. Get the next one, please. Yeah, the next one, please. These are all different microstructures you can get with the M in bulk HEA in a different alloy. And this is an interesting mechanical property of bulk aluminum, cobalt, chromium, iron, nickel HEA. So look at the true stress and true strain values. The red one is the electron beam melted selected electron beam melted product, and the black one is for the cast material using normal methods. So you see the tremendous improvement in properties, in case of the the melting processes employed in the additive manufacturing process. Next one, please. Well, again, it's a material space for different kinds of HEAS. You can see you have a big menu in front of you. You can choose. The material space is really quite big, and you can figure out what property you want and choose your material accordingly. Next one, please. So, what is the future of high entropy alloys produced by AM? Now, high entropy alloys promise to have high potential as functional and structural materials, and due to their properties which I've already told you. And they are also being considered as very good hydrogen storage materials. So this is an important point. Now, traditional manufacturing methods of HEAS, which are arc melting, spark plasma sintering, these are limitations with respect to chemical homogeneity and shape and size of the bulk material. These are the incentives for using AM for HEAS. This is the reason why we should use AM for processing of high entropy alloy. AM will also be cost effective with much better control on shape and size to produce HEAS with desired microstructure and property. You can have an end product, finished product by AM process because everything is controlled by the CAD program. So once you set up everything, it can be completely automatic, and you'll have your product one after the other. Next one, please. So what is the way forward? Now, researchers indicate that there's a vast scope of attaining exceptional mechanical performance from additive manufactured product, produced HEAS, by optimizing the materials and processing parameters. And what are these? The powder size distribution, thermal gradient, and solidification velocity. Now, some theoretical understanding is still lacking about the melt-pool physics and the liquid-solid interfacial behavior. So these are the areas where a lot of work should be done. And the other thing is, there will be some highly beneficial post-manufacturing heat treatment, which should also be taken care of. Yeah. So I thank you for your kind attention. If there are any questions, I'd like to answer them.
So thank you for such a detailed and insightful presentation on 3D printing of HEA, high entropy alloys. I would now like to invite Rhythm for addressing the questions that we have garnered from the audience. Over to you, Rhythm.
Thank you, sir, for your presentation. Now I will put forward the questions for you. The first question is, what is the prospect of 4D printing in high entropy alloys?
Can you tell me once again?
What is the prospect of 4D printing in high entropy alloys?
Yeah. Of course, it will be an extension of the 3D printing process, right? So should not be any difficulty with the high entropy alloys. You can do it with other materials. You can use with these materials also.
Sir, you are not audible, sir.
Pardon?
Sir, you are not audible, sir.
How come?
No, he is audible. It's okay.
Yeah, right.
Okay, sir. Okay, sir. Over to the next question.
Right.
What is the prospect of high entropy alloys in biomaterials?
There's plenty of prospect in biomaterials, as I already showed you one slide where orthopedic implants are being made, and people are working in this area, one thing you must realize that the high entropy alloys came into being only in the year 2004. It was Professor Brian Cantor in Oxford University who first reported about it, and at the same time, Professor Ye of Taiwan, he also reported about these materials. So a lot of research is going on, and there's a huge scope of high entropy materials being used as bioimplants. You see here, you have a choice amongst a number of elements. You can find out in a particular area where you want it, how it is going to react with the body fluids and all that, and choose your elements accordingly. So, of course, yes, there's a huge scope of using HEAS as biomaterials.
Okay, sir, over to our next question. Does high entropy alloy research fundamentally changes alloy physics from enthalpically driven to entropy driven materials design?
Yeah, you can say so. You see, the whole concept of alloy is changing. As I already told you, we used to think of an alloy with a solvent and one or more solids. So here, which element is a solvent? There are 5 or more principal elements. So the entire thing is, presenting a scenario which metallurgists even a few years ago couldn't even dream of. You see, for example, look at the scenario. You have got 5 elements, 5 or 6 elements. Now, you see, if you are in a crowd of 100 people, say during a meeting or during a dinner or during some celebrations, you will find there will be small groups. Like-minded people will group together. So you'll have a cluster of 6 persons here, a cluster of 10 persons there, etc., etc. So what is expected? That when you're dealing with 5 or more principal elements, there will be some kind of ordering in the alloy. So there is a chance of short-range ordering on a mass scale in the alloys. There are some experimental results that yes, these short-range orders are happening on a mass scale, but experimental verification is not that good yet. So I have a feeling that we'll be able to find out much more about these materials with time. But what you said is correct. We have definitely in this, we consider these materials, we are changing gear from enthalpy control to entropy control. Yeah.
Okay, sir. Our next question is AM effective for mass production of materials?
Absolutely. Additive manufacturing is very much capable for mass production of these. You see, when you do ordinary melting of high entropy alloys, because there is so much of difference in the densities of the different elements, there could be problems. Inhomogeneity is a very big problem. But in case of the additive manufacturing, this problem is obviated because you have very quick melting that takes place. And you see, even very complicated designs can be made because the whole thing is controlled by the CAD. So, and if you have a CAD machine, and if you have got this kind of equipment, you can produce a lot of these within a very short time. And for mass production, it will be ideal, definitely.
Okay, sir. Thank you for your session.
Thank you. Thank you very much. I really enjoyed.
Yes, sir. Team Reminiscence is really grateful to you for your contribution and joining us on our celebration of 8 years. And we thank you so much for clubbing these 2 very recent topics of additive manufacturing and high entropy alloys together and giving such an insightful talk on this. Thank you, sir. Thank you again for joining.
Thank you all. Thank you very much.